Hello everyone, how are you? I hope you are all doing well. So in today's lecture, we are going to study what happens when AC voltage is applied to a resistor. Okay. So in that case, we are going to studying that what will be the current flowing through the resistor R and what will be the power dissipation along the resistor R. Okay. So till now we have studied when any like DC source is applied, but in this case the case is little different because here we have applied an AC voltage, and that voltage is V equals to V naught sine omega t, where omega is the angular frequency and V naught is the maximum voltage, and V is the voltage at time t. Okay, sometimes it is written as the function of time also because we can see that it is a function of time. V at t equals to V naught sine omega t. Okay, so now for finding out the current, what we can do, we can apply Kirchhoff's loop rule. Okay, according to the loop rule, we can uh, uh, we can uh, we can find out the current which is flowing through the resistor R, and as we know that the Kirchhoff's loop rule, or we can say KCL, okay, sorry, KVL means the Kirchhoff voltage law. In according to that, we know that the total sum of voltages difference for a closed circuit is always zero. So that's why let's apply Kirchhoff's loop rule. Okay. According to that, we will start from the external source, AC source, and then we'll move to the resistor R. So it will be minus of V plus, because we are moving in the direction of current flow. So that's why it will be plus, and IR equals to 0. This will be the equation. And finally, we will get the equation as IR equals to V. And now let's place the expression for voltage V. So it will be IR equals to V naught sine omega t. Now we can find out the equation for current at time t. So that will be I at t equals to V naught upon R sine omega t. From this equation, we can say that the value of V naught and the resistance R both are constant. So that's why let's assume another constant as per our equation. So we can assume it as assuming I naught equals to V naught upon R. So the above equation will be found as current I at time t is I naught sine omega t. So this will be the equation of current at time t. And if we compare current and voltage, what we can say, this will be the current flowing through the resistor R at time t. If we see the voltage which was V equals to V naught sine omega t, and here the current is I equals to I naught sine omega t. So we can say that both current and voltage both are in phase. That means the phase difference between them is zero. And the only difference is the difference of amplitude. Here, in case of voltage, the amplitude is V naught, and in case of current, the amplitude will become as I naught, and which is I naught equals to V naught upon R. Fine. That means there is a change in amplitude, so their graph will be sinusoidal, but their amplitude will be different. Okay, so let's draw their graphs, and then we will get some idea. Okay, here voltage and current, are in phase. Okay, or we can say that phase difference is zero. Phase difference is 0 degree. Now the graph of current and voltage is, let's draw the graph. Then it will look like, wait 1 second. Okay, so first of all, let's draw the graph for voltage V. So it is a sinusoidal graph, so it will look like time t, and we are plotting the graph of voltage V. Wait, I'm let me draw it again. The graph will look like, sorry, 1 second. Okay, so the graph will look like this. Okay, and the maximum voltage here is V naught. Okay, now we can draw the graph of current, and that will be, because its amplitude will be less than the amplitude of voltage, because the amplitude I naught is I naught equals to V naught upon R. So that's why the graph will be little lower than the amplitude of voltage. Okay, like this. It will be the graph of current. Okay, now let's name them. That's why, or we can say you will be getting easily that which is the graph of voltage, and voltage V equals to V naught sine omega t, and the blue one is graph for I equals to I naught sine omega t. Here the amplitude of current is I naught. So that's how we can draw the graph for voltage and current. Now our task is to find out what is the instantaneous power dissipated across the resistor R. Okay, so power dissipation. Now instantaneous power is written as P equals to I square R. This will be the equation for instantaneous power. Now let's place the equation, we can say expression for power, equation for current I in this equation. So finally we will get I equals to I naught square sine square omega t into R. And if we take constants aside, then it will be P equals to I naught square R sine square omega t. This will be the equation. So it will be the equation of instantaneous power. And now we are interested to find out the average power. What will be the average power of the system? Okay. So now Average power. How to find out average power? Both of the side take time average over one cycle. Okay, over one cycle. So it will be average over I naught square r sine square omega t. So as we know that average of a constant quantity is that same constant only. So it is I naught square r. Now the quantity which is changing with time is sine square omega t only. So that's why we have to take average on that particular quantity. I know sine square omega t. Now, as we know that, as we know that the average of sine square omega t is half. We can determine it also, but see, when you are doing any like the physics derivation and all, then you don't need to derive all these things because these are called as like mathematical tools, or we can say uh, the mathematical identities we are going to use here. We are not going to derive each and everything small in each and everything like the whatever the we can say helping tools we are using here. So we are going to use directly. Now, uh, the equation of power will be average power P equals to I naught square R into half. So the equation will be average power, or sometime it is written as P average also. So it will be half I naught square into resistance R. So this will be the equation of average power. And we can see that it is not depending on time. It is constant quantity. And we know one another relation also in terms of IRMS current. Since we know that IRMS is nothing but I naught by square root 2. If we square both the sides, then we will get I square RMS equals to I naught square by 2. Now, if we place this equation in the above equation of power, then we will get the equation of average power in terms of the root mean square current. So it will be average power P equals to IRMS square into resistance R. So this will be the equation of average. This will be the equation of average power. I hope you understood these two derivations. First one was for like current, how to determine the current I which is flowing through a resistor R where the external AC source is applied. And the second one was instantaneous current, and its another part is average power. Still, if you have any doubt, then you can ask in the comment section. I'll be happy to answer them. Thank you.